All right, section 9.2, we are looking at multi-stage experiments, and the method for drawing these, we talked about last time, most of the time, is a tree diagram, but there are occasionally some places where some alternate versions make some sense and maybe make even maybe a little bit more sense than a tree diagram. So we're going to take a look at the first one, example number 2. We have a box and it contains 5 slips of paper, numbered 4, 6, 7, 8, and 9. A player reaches into the box and draws out 2 slips of paper and adds them up. So we could draw out a tree diagram for this, right? We just have to draw a tree diagram where it shows what they drew the first time, and then draw branches off of that for what they drew the second time, and add the things together the way that they're describing. But there are other ways of doing this one too, and so I want to show you an option for this one that works pretty nicely. So what we're going to do is, instead of drawing it out, we're just going to list them out. For example, if I draw a 4 out, then I'm not putting the 4 back in. I'm just keeping it, right? And then I draw a second number out. Well, then I could be drawing out a 6, right? Or if I drew a 4, I could draw a 7. Or I could draw a 4 and an 8, or I could draw a 4 and a 9. And those are all the ways that I can draw a 4 and something. So I've explored every possibility to combine with a 4, and I don't need to write the 4 down anymore. So now I will go on to the 6, and I don't need to write 6 and 4 because I've already included that possibility. So I could do a 6 and a 7, or 6 and 8, or 6 and 9, and you notice there's 1 fewer than there were before because we don't have the listing of the 4. So now I'm not going to list 4s or 6s, so I can do 7 and 8 or 9, and my last option is 8 and 9. So these are all of the possibilities. Okay, so it's just drawing it out or listing it out instead of drawing it out. That's the difference in what we're doing. They're all equally likely because there's 1 slip of each number in the basket, right? It doesn't matter which piece I draw, it's equally likely to be drawn as a different piece. And we can actually go through here and we can add them up, and that's what we'll do next, and see what we have to answer the questions that follow. So I'm just spacing them out a little bit. Okay, so we're going to add these together, and I'll just write it in blue. So 4 plus 6 is 4 plus 7. 4 plus 8, 4 plus 9, good, 13, and then 14, 15, and then 15, 16, and the last one is 17. And what we're asked for is that we get evens or odds. That's what we're comparing anyway. It says that we win if the sum is even, and if it's odd, we lose. And so the player wins in the number of times that they can get evens. So I'm going to go through and just find all my evens. So I think I found 4 of them. Did you find 4? Okay, 4 out of how many? 10. So if we count up all of our different options of what could have happened, there were 10, and this reduces to 2 over 5. So don't everybody answer at once. Yes, 2 out of 5. All right, does that make sense? Okay, so we're going to take that same scenario, but we're going to change the question. It says, does the probability change if the 2 numbers are multiplied? So just because I get an even number when I'm adding doesn't mean I get an even number when I'm multiplying. So I'm going to go back and I'm going to figure out which ones are even when I multiply. So if you want, you can actually, multiply everything together to get, the results, just like we just did. That would be perfectly fine. But I think there might be an easier way to do that. How is it that when you multiply 2 numbers, you get an even number? Do you know?
If it's multiplied by an even number?
Yeah, if one of the numbers you're multiplying is even already. So if we go back and we pick all the times that I'm multiplying with even numbers, which is all the first 4 of them because they all have 4 in them, it's all the next 3 because they all have 6. And then I have my 7 and 8 and my 8 and 9. Lots of even numbers, right? Yeah, in fact, how many?
9.
Does the probability change? Yes, sorry. Yeah, 9 out of 10. There's 9 out of 10 ways if we are looking at multiplication fact that gives us an even number instead of an addition fact. Is that all right? Okay. The next one is kind of similar in how I'm going to draw it out. It talks about a spinner. We have two spinners, in fact. So our experiment consists of spinning the first spinner, followed by the second spinner. And we're assuming that each of the angles is even. So like on the first one, it's a 50-50 shot. On the second one, it's 1/3, 1/3, 1/3. Does that seem reasonable? Okay. So it says first to find the sample space. That is, what are my options? So you could draw out a tree diagram here. It wouldn't be a bad one to do. So let me just sketch what that would sort of basically look like. And then I want to show you what we also could do instead. So you could draw out a 1 and a 2, right? And then off the 1 and 2, you could make 3 branches and do a 1, 2, or 3. Does that make sense? And since it's a 50-50 here, right, these are 1/2s, and these are all 1/3s, they're all going to give you the same product if you multiply along the branches. So this is perfectly fine. Another option that works really nicely for this one, and it looks kind of like the last one, is to actually list out the items, and it fits in with Part A. Part A says to find the sample space. So sample space means a listing of items. And because all the items are equally likely, it's why we actually don't have to have a tree diagram on this one if we choose to do it this way. So one outcome, of course, is that I spin a 1 and a 1, or a 1 and a 2, or a 1 and a 3. Those are all the ways I can spin a 1 first and then spin something else. Or I can start out by spinning a 2, and then what are my combinations? 2, 1, 2, 2, and 2, 3. So all the first ones are coming from here, all the first 2s are coming from here, and then the 1, 2, 3s come from over here. So I've kind of listed them in ordered pairs. Do you have to list them in ordered pairs? Well, not necessarily. You could list them just as like the numbers, like almost it looks like 11, 12, 13, 21, 22, 23. That would be okay. There's not a specific way that it has to be done for it to be done, sort of correct. These are my options, though, and whether or not you think about it from the perspective of this sample space or from the perspective of the tree diagram, your answers will be the same for the part B, I, double I, and triple I. So we're going to go back and we're going to look at the probability of spinning 2 even numbers. So each of these are equally likely in the sample space. So how many 2 even number places are there? 1, just this one, right? The 2, 2. So if I'm looking at even numbers from that sample space picture, this is a 1 out of how many choices were there over here? 6. So you can do 1 out of 6. If you're looking at it from the tree diagram, you're looking at spinning a 2 and then a 2, and then if you multiply along those branches, you're going to get 1/2 times 1/3 is 1/6. Okay, so they match. Spinning at least 1, 2. What does at least mean?
One of them has to be 2.
One of them has to be 2, but they could both be, right? So at least 1 means 2, 1, 2, or more. So it's all of those. Yeah, we got 4 of them. So on double I, we have 4 out of 6. 4 out of 6 would reduce to 2/3. Now I want to talk about the tree diagram real quick because we haven't seen this happen yet. But along our tree diagram, we would actually have the branch that goes 2, 2, or 2, 2, 1, or 2, 3, or 1, 2. These are the 4 different branches, and they're all 1/6 individually, and if we add 1/6 together 4 times, we get 4/6. So we mentioned it last time, but we didn't have the opportunity to see that the way that we take multiple branches and find out the probability of it being on any of those branches is that we add up the probabilities of each of the branches. This one just happens to be that each of the branches' probabilities are equal. So it ends up being the same as multiplying by 4 branches. That doesn't always happen. Our last one, spinning exactly 2, 2. Exactly 1, 2. Yeah, 3. So we wouldn't have this one, right? If that were the description, we'd eliminate that. So we have 3 out of 6, which reduces to 1/2. All right, any questions on that?
I do. Why don't we do like in the pairing on part A, like 3-1, 3-2.
We're spinning this one first, and then we're spinning this one second. So the first spinner doesn't have a 3 on it. Okay, I'm only spinning the one that I've highlighted in blue. This one, this spinner right here is my first spin. I can only get a 1 or a 2 from that spinner. I don't have a second, I don't have a 3 on that spinner to get.
Right, but how do we get the 3 like in the other ones then?
Because this is my second spin, and on my second spin, I can spin a 3. So if I spin this spinner and I write down the result, and then I spin this spinner and I write down the result.
Like a 3 can't be in the first spin.
No, because the first spin is the first spinner and there's not a 3 on it.
Okay.
So it has to be correlated to whichever spin I'm looking at. Now, the question could be asked in reverse, right? Like, what if we spun the spinner on the right first and the spinner on the left second? And if we did, then all of our ordered pairs that I wrote down would just look like they flipped. Yeah. Okay. I wrote this problem a really long time ago, and it might fit more accurately with my 8-year-old daughter now, so we'll go with it. When I purchase a new shirt for my son, there is a 0.15 probability that he will stain it the first time he wears the shirt. If the shirt is stained, there is a 0.2 probability that I will not be able to adequately remove the stain. Hence, it's permanently stained forever, right? That's what that says. What is the probability that my son's new shirt will be permanently stained the first time he wears it? All right. So I throw this one in here because I want you to understand that tree diagrams don't always have to have the same number of branches off of every branch. The 2 that we've seen so far did, right? We had 2 branches over here, and then they each had 3 extending from them. But it doesn't have to work that way in a particular problem, and this is the case where one does not. For example, there's 2 things that happen the first time my son wears the shirt. What are they? Yeah, it's stained, or there's no stain. And if there's no stain, then it's already not permanently stained forever, right? So this is the no stain part is really like the end of the branch. There is nowhere else I need to go. The shirt's in good condition still. Whereas the stained shirt, I have to extend the branches one more time because now I have to treat the stain. So there's 2 outcomes that can happen after I treat the stain. What are they?
And it will be permanently stained in that this or that.
Okay, so it's either permanent or it comes out. Some kind of language like that. Does that make sense? Another reason I like this example is because it's the first one we've seen where we are using decimals. And there's nothing wrong with using decimals inside of tree diagrams too. This one gives it to us that way. But even on some of the other ones that haven't given it to us that way, we could have used them along the way as long as we don't get any repeating decimals. Okay, we're not going to do that with those because then we have to approximate things. So this one doesn't have that feature. It says if he stains it, or what's the probability that he stains it? 0.15. So if there's a 0.15 probability he stains it, what's the probability he doesn't? 0.85. Nathan, how'd you get that? Yeah, and I also mention this one right here at this point because I want you to remember that every set of branches that comes off of a single node, that's what this thing is, have to add up to 1. They have to represent all the probabilities. So I can't have like a 1/5 and a 1/5 because I'm missing 3/5 if so, right? Like I got to have all of it add up to 1. All right, we have 2 more branches to fill in. If he stains it, it's either permanent or it comes out. What is the likelihood that it is a permanent staining? 0.2. What's the probability that it comes out then? 0.8, because once again they have to add up to 1. So this is the tree diagram that would be representing this particular problem. And I'll reiterate one more time, even if it doesn't say that you have to show a tree diagram or some kind of similar work like we did over here, you have to. That's part of the showing your work process for this particular section. Okay, you're going to be drawing lots of tree diagrams, so make sure you have your space to do that. Now we're going to answer the question. The question actually wants to know, what is the likelihood that my son's shirt will be stained after the first time he wears it forever? So it's got to be stained first, and it has to be permanent. So this is the path that answers that question. So what would I do with the 0.15 and the 0.2? Yeah, it'd multiply them. So what is 0.15 times 0.2? 0.03. It's not very high. That's okay. These are made up stats. There's no way this is real. All right. Any questions on that one? Kind of unique. Yes, Braden.
Why did we have to show the tree diagram whenever we could just multiply them?
So we're doing it for a couple of reasons. Number one, because that's what your kids that you're teaching at this age would be doing in order to figure it out. That's the primary reason. The secondary reason is because generally we don't just have one question that we're asked from a tree diagram. It's more like this one where there's several questions. And if I've only drawn out a portion of it or only done the answers for a portion of it, it's not always easy to find the other pieces.
Okay.
Yeah. Okay. Joe. Joe says, if a family has 2 children, the only possibilities are 2 boys, 2 girls, or 1 of each. Okay. Because there are only 3 possibilities, the probability of having 2 boys is 1/3. Is Joe correct? Explain. So there's pieces about what he says that are correct. I mean, you really can only have either 2 girls, 2 boys, or 1 of each. I mean, like that part sounds good. The question is whether or not that means they're all equally likely. So what do you think? They're not equally likely. We're going to do a tree diagram to show it out, but I'll actually show you work in another way too, just so you can see a couple of options here. So when you have a child, the first child, right, one of them at a time, even if you've got twins, it's still one at a time we're talking, right? The child has 2 options. We've got a boy or girl. After that, I mean, that's child number 1, right? It's one or the other. And then we have a second child, so we're just showing out all the possibilities, not necessarily a specific family, but all options. We have child number 2. We also have a boy or a girl. And what are the probabilities along these branches?
1/2.
Yeah, they're all 1/2, every single one of them. So feel free to use 0.5 or feel free to write it as a fraction, your choice. It works very nicely both ways. Like this. So if I looked at the probability of having 2 boys, what is it? It is 1/4. What is the probability of having 2 girls? Also 1/4. And notice what happens in between here. There are actually 2 distinctly different ways I can have a boy and a girl, right? Because the order of those ages and those children would be different. One is having a boy first and a girl second. The other one is having a girl first and a boy second. So each of these are also 1/4. But if you consider the probability of having 1 of each, what do you actually get? No.
1/4.
2/4, which is, yeah, Elizabeth said it is 1/2. So when we go along these branches there, right, we multiply by the 1/4 or 1/2 times 1/2 to get from the 1/4. But at the very end, when we're combining branches for whatever description we want, we add them together. Is that what you're about to ask? Yeah. So it's kind of like what I was talking about over here on this one, where if I go along all those red pieces and I add 1/6 plus 1/6 plus 1/6 plus 1/6, I get 4/6. same thing. If I want the result of combining all those branches as my sort of like desired outcome or whatever, I would add the final branches probabilities together. Now let me show you one other way you can think about this one that works pretty nicely. Whoops. I'll shrink it so that I have a little more space. Instead of doing it as a tree diagram, it works really pretty nicely to do it kind of like we done this one where we write them as ordered pairs. And you could do that. And I'll write them as ordered pairs but without the commas this time just to show you another version. Is that you could just list the options, right? I could have a boy and a girl, or I could have a boy and a boy. I could have a girl and a girl, or I can have a girl and a boy. And it doesn't really matter what order in which you calculate them. There are 4 outcomes, right? But the thing is that 2 of the outcomes actually have one of each gender. So we need to answer Joe. We haven't done that yet in like words. But this is sort of the supporting work to show why it's not going to hold like this for him. So Joe is incorrect. And he's incorrect because there are 4 ways to have 2 children. And I'll just list them here. We can have the boy boy, the boy girl, the girl boy, and the girl girl in whatever order you like. Hence, the probability of having 2 boys, which is the one he described specifically, is actually 1/4, not 1/3. Again, remember, we're looking at an entire family structure, not at the individual birth of each child. The individual birth of each child is still 50-50, but it's what happens after you've had the children and those things. Another way you can think about it is if you examined all families that had 2 children, every single family. You collected all their data. About 25% of them would have 2 boys. Right? About 25% would have 2 girls, and about half of them would have a boy and a girl. Yeah. All right, the next example is actually a real-life example from my life. Huntington's disease. Anyone familiar with Huntington's disease? Abby is? Okay. So Huntington's disease is a degenerative disease that runs in my family. My grandmother had Huntington's disease. She passed away in 2005. In 2000, and my father had Huntington's disease as well. He actually passed away in 2014. In 2001, my parents decided to tell us Grandma has Huntington's. She'd been misdiagnosed for a long time with several different things, but they had known for a while that this is what she had, and they finally decided to tell us. The probability that a child will have Huntington's, given that one of the parents has it, is 0.5, and I have 2 siblings. So let me just tell you just a little bit about Huntington's so that you can have a greater appreciation for the significance that this scenario really plays in my life. So Huntington's is a degenerative disease. It overproduces a chemical. I'm probably not saying all the sciencey stuff right, so don't go quote me on this. But it overproduces a chemical that gets in the way of your central nervous system. So what happens is that over time, your central nervous system starts not working right. So balance is one of the things that kind of starts to go. So I remember my grandma slipping and falling really easily. Your ability for your brain to tell your other, body parts what to do. So like I have a very distinct memory of her at a Golden Corral not being able to stop the ice cream maker before the ice cream was all over the place. Driving becomes untenable. Because you can't stop when somebody in front of you stops quickly enough. And so eventually both my grandmother and my father lost their licenses because they couldn't safely operate vehicles anymore. But not before my dad managed to total a couple of different motorcycles. My dad was a very a very active man. So this was also very difficult because he was so active. The dad that I remember from my childhood was the one who would drive his motorcycle down to the Gulf shores, and then drive him back all in one day, like all the way down to the Gulf of Mexico, like crazy stuff. Or he would ride bikes. He would go out and he would ride his bike 100 miles, or not 100 miles before church, but some mornings he'd go out and he'd ride, 25 miles, and then he'd show up and make coffee for a Sunday school class at church. Like, he was just a very active man. So what Huntington's does is that it limits your ability to do functions. So my dad got to the point where swallowing, and my grandma did too, swallowing became almost impossible. And if you can't swallow, you can't drink, you can't eat, and your body starts to deteriorate, obviously. And so at the point when my family decided to share this with us, they only shared it with us because there had become new scientific ways to ensure that if you had Huntington's, that you did not pass it on to the future generation. And it's things that and you know about them from other sources, and it has to do with in vitro fertilization. So everybody has the Huntington gene, and it's whether or not there's enough triplet repeats of the A's and T's and G's and whatever letter I'm missing. And if there's enough of them on this particular gene, you'll either have Huntington's, which is what my father had, or you'll have or you'll have the ability to pass it on. So you get one of these genes, unless your genes mutate, of course, because that is where these things come from to begin with. You get one of these genes from your father, and you get one from your mother. And I'm sure that your science professor is going to tell you much better things if you ask her how to describe this. But you get one from your dad, one from your mom. So my grandmother had a mutation because none of her family has this at all. And she had not only the gene that had Huntington's, but she also had the gene that passed it on. So she had two children, my dad and my aunt, and my dad actually ended up getting the gene that had it, and my aunt ended up getting the gene that passed it on. My aunt never married until she was until she was actually 50 years old, and so she didn't have any children. So it's kind of a moot point for her on her genetic structure after her. But for my father, we have 3 children in our family, and so each of us has a 50-50 shot of passing this on. At the point when they told us, I had been married for almost 3 years, and my family knew about it long before I ever got married. My sister had been married for almost 1 year, and my brother was seriously dating the woman that ended up becoming his wife as well. So they tell us this at Thanksgiving. Yeah. By the way, let's have a family discussion. Thanksgiving 2001. And my husband and I were living in Kansas at the time, so we were just visiting. But they told us all this, and they told us this because what they could do is they can actually, do in vitro fertilization. They fertilize, everything, and they create the embryo, and then they grow the embryo to 8 cells. And once you grow the embryo to 8 cells, you can test whether it has the genetic, disease for Huntington's or whether it doesn't. And then the idea behind it then is that they would only implant the embryos that don't have it. And then you're left with this ethical dilemma of what to do with the other embryos. So my husband and I looked at each other and said, we can't do that. We're not going to make that decision that's not the route we're going to go. That's what we decided that evening. But this is what went through my mind with these numbers as my family shared this information that evening. So I'm the oldest. So this one's me. And there's 2 possibilities. This is almost identical to this problem over here with the boys and the girls. There are 2 possibilities. I either have it or I don't. So I'm just going to call it H and D, okay? And each of them are a 50-50 chance. I'm going to use decimals this time, so I'll do 0.5s. My sister is the next in line, and so these next set of branches represent my sister and the possibilities for her. Again, she either has it or she doesn't. And each one's a 50-50. And the last one is my brother. And again, the reason that this is all happening in this sort of way that it looks like, well, I don't know, lots of people or something, is because you're looking at what happens after you have the 3 kids at the different possibilities that could exist. But only one of these exists, okay? And again, they're all 0.5s. And the first question on the next page, don't turn just yet, but the first question on the next page is the one that was running through my mind the whole time was, what is the likelihood that all three of us are going to come out with it, with not having this? We're all going to be okay. And that's what I want to know. So my dad, when he passed away, was 50, how was he? He was 50, like 55. That's probably not exactly right, but he was in his 50s. And the age of onset is approximately the same age of onset as your parents. My dad was showing symptoms in his 40s, which means that if I had it, that I'm in my 40s now, so if I had it, I'd be pretty close to showing symptoms as an average. But we haven't really gotten there yet, but this is with a standard deviation of 18 years, which means that it could be 18 years later, or it could be 18 years earlier that you show symptoms, and about 68% of the population will be within that 18-year span on either side. It's a very big standard deviation. It's huge. It almost makes it worthless to know the age of onset. It really does. It's crazy. But this was the number that kept running through my mind right here. What is the likelihood that we don't all have it? And that's the first question. It says, what is the probability that at least, well, it's the reverse of that. What is the probability that at least one of us does? Well, the probability of at least, one of us having it is a complement. It's 1 minus the probability that we're all okay. What's the likelihood that we're all okay? Well, it's 0.5 times 0.5 times 0.5. And what is 0.5 times 0.5 times 0.5? Nathan's getting it for us. Nope.
0.125.
Mm-hmm. And what's 1 minus 0.125?
0.875.
It is. It's an 87.5% chance that this disease continues in my family at least one more generation. That's high. And that scared me. It scared me a lot. And it scared me enough that my husband and I said, we're not doing any kind of genetic, or we're not doing any kind of in vitro fertilization. But if I have Huntington's, we're not having children. Because it's an awful disease. It's really, really awful. And I wasn't going to push it on a future generation. That was the decision that my husband and I made. And so that was the first time that we jointly at least came to the decision that adoption was really part of the options for our family. And, it still, I would say at that point was, a plan B for us, right? Like it wasn't what we were going into this thinking, but it was definitely going to be what happened if I had Huntington's. So in 2003, 2 years later, I tested for HD, for Huntington's, and I do not have the disease. That's why we have our daughter Abby. But that 2 years and thinking upon that and God working on our hearts really made it very clear that no matter what happened with the outcome, God wanted us to adopt. And it became a plan A. It was part of what was going to happen with our family. And as you know, we have 5 adopted kids now with 2 more on the way. So my dad's in heaven, and his mom is too. And I know that they are happy to see that something good came out of it. Because that's what God does. He takes things that are really hard for us, and he brings good out of them. I do still have 2 siblings, and they have lots of kids, actually. Between my 2 siblings, they have 5 children. And neither of my siblings has ever been tested for Huntington's. My sister almost got tested, but at the point when she was going to, she found out she was expecting, and she didn't want to know. That's kind of what it is. She didn't want to know. And so My brother made the decision that he wasn't going to let any of that interfere with just the natural progression of life, and that's okay too. But I do have 2 siblings that are still both considered at risk, and 5 nieces and nephews. So the last question we're going to look at today is, what is the probability still that at least one of my siblings has the disease? So it's the same question that we asked before. It's 1 minus, or well, let me write it this way. The probability of at least one is 1 minus the probability, the probability that no one has it, that we're all okay. Probability of being okay. The difference is that at this point on this diagram, this whole diagram doesn't exist anymore. The only part of this diagram existing is down here, because I don't have it. So none of this happened. It eliminates those 4 options is what it really does. And it doesn't even eliminate this, or well, it doesn't eliminate the D, it eliminates the 0.5. It's a 1 now, because I did the testing for it. So I have this bottom piece of the branches, and we're still now looking then at the probability of that red piece at the bottom. So we have now 1 minus just 2.5s multiplied. So what is 0.5 times 0.5? You should know that one. 0.25. And what is 1 minus 0.25? 0.75. So there is still a 75% chance that at least one of my siblings has Huntington's disease.